let us talk about and just remind ourselves an important symbol and vocabulary word. Remember, you'll often see this symbol. It's the Greek letter epsilon, I believe. And you'll often see it in problem statements that might talk about the EMF, which is short for electromotive force, but as we talked about last week, all those things on the bottom there mean the same thing. EMF is the potential difference across the battery, which is the voltage of the battery, et cetera, et cetera. So keep that in mind. It can get confusing because of the different words we use, the different symbols we use. But these are all pretty much synonymous. They are synonymous when we talk about DC circuits. All right, let's talk about something interesting. You look at this circuit here, and you know how the current's going to flow through. We've already talked about that. If I were to take the current passing through resistor 1 and multiply it by the potential difference across resistor 1, what happens here? Well, let's just kind of do what we call a unit analysis. We've done this before, I believe. Current is measured in amps. Potential difference is measured in volts, right? Amps times volts. But what is an amp? And the amp is the flow rate of charge, and 1 amp is a coulomb per second. What is a volt? A volt can also be thought of as a joule per coulomb. Interesting. So coulombs per second times joules per coulomb, what's that going to become? It's going to become joules per second. Joules per second. Wait a second. Wait a second. Get it? We've heard this before. This is simply 1 watt. Okay? And a watt is a measure of what? Power. Right? The basically usage rate of energy, you could think of it that way. So when we want to figure out the usage rate of energy for circuit elements, one of the ways to do it is take the current passing through that circuit element and multiply it by the potential difference across that circuit element. Okay, there are a couple other ways I'm going to show you here in a moment. And so right here in the middle, power equals current times potential difference, I squared R, V squared over R. Notice these all mean the same thing. Okay, electrical power is what we're talking about here. And why do we have 3 equations? Just remember Ohm's law from last week, I equals delta V over R, which oftentimes is written as V over R. Okay, if you use that, you can basically substitute in to get any of these 2 values to equal power. So this is really important. This is on your data booklet. I keep talking about data booklet. You have an equation sheet. Those who take an HL Physics, you will get a data booklet. What is the unit? We already talked about it, but it's the watt. 1 watt equals 1 joule per second. So a 60 watt light bulb is in an electrical circuit where it basically uses up 60 joules of energy every second, et cetera, et cetera. So you can think of this power, electrical power, as being what is delivered by the battery or batteries or being consumed by an electrical component. It's synonymous in that sense, or it means both things, I should say. It's not synonymous. Okay. So let's do a sample problem with this. 2 sample problems. First of all, a light bulb draws a current of 0.5 milliamps. The potential difference across the bulb is measured to be 1.4 volts. What is its power consumption? Let's do it together here. Number 1. So we're given that the current is 0.5 milliamps. We're also given that the potential difference is 1.4 volts. So it looks like we would use this iteration of the equation, P equals IV, 0.5 times 10 to the negative 3 amps times 1.4 volts. Go ahead and do that in your trusty calculator. Some may be able to do it without a calculator. What's a half of 1.4? That's just 0.7 times 10 to the negative 3 watts, right? Half of 1.4 is 0.7, which is basically you could call that 7.0 times 10 to the negative 4 watts, or you could call it 0.7 milliwatts. Any of those would be equivalent. Okay, number 2, the potential difference across a 30.0 kilo ohm resistor is measured to be 18.0 volts. What is its power output? So in this case, what are we given? We're given the resistance is 30.0 kilo ohms, and the potential difference is 18.0 volts. So I have resistance, I have potential difference. So it looks like the best equation to use in this case is this one, which again, remember delta V and V are synonymous when we talk about these DC circuits. 18.0 volts squared divided by 30.0 times 10 to the third ohms. So it's a little more challenging. I'm going to revert to my calculator. And I get a power of 0.0108 watts. Yeah, or I could call it 1, 2, 3, that would be 10.8 milliwatts. Okay, so there you go. You can see 2 sample problems where we use this information. Notice there's a lot of versatility in this. If I know any 2 of those values, 2 of the 3 of current, potential difference, or resistance, then I can basically figure out the power output. Pretty nifty. It's quite powerful. Okay, there you go.